Good day, everyone. Today, we will tackle about polar curves and double integrals.
But first, let us find out what polar coordinates are. Polar coordinates are complementary system to Cartesian coordinates, which are located by moving across an x-axis and up and down the y-axis in a rectangular fashion. We'll be using this polar equation, r is equal to 4 sine 4 theta, to our Desmos calculator.
So, what is Desmos? Desmos is a math ed tech company building calculators, digital classroom tools, math activities, and curriculum for classrooms around the world. Desmos wants to build a world where every student learns math and loves learning math, where students access the power of beauty of math doesn't depend on their place of birth, race, ethnicity, gender, or any other aspect of their identity. We have now our polar equation and I have the following observations. Since we use the function sine, we have the first case where if our coefficient of theta or n is even, the number of petals that can be shown in the graph is twice the number of n, or simply 2n. That is why in our example we have 8 petals or curves in total. The second case is when our n is odd, then the total number of petals or curves is the same as n. If we change this coefficient of theta into 3, we will have 3 petals in result. In addition, our coefficient of sin theta determines the size of each petal and its distance from the point to the origin. So if we will change this coefficient of sin theta into 2, 3, 4, 5, or 6, we could see that each petal changes its size. I also observed that if our n is 1, -3, 5, -7, 9, -11, and so on, we can clearly see that there exists a petal that touches the upper part of the y-axis. So if we will change this part into -3, we could see that it touches the upper part of our y-axis. And if we change our n into -1, 3, -5, 7, -9, 11, and so on, we can see that there exists a petal that touches the lower part of our y-axis. So if we will change this -3 into 3, we could see that it really touches the lower part of our y-axis. I am now done with my test. So may I now call Mom Irish to explain on how to get the area of one curve?
Wow, that was a very good presentation, Miss Hazel. Thank you for sharing your very keen observation on the polar equation. And now, since Miss Hazel are now done with presenting the observation and demonstrating it in the Desmos app, at this moment, I will now explain and present to you on how to solve for an area enclosed by one petal of the polar curve. Since we already have a polar equation, which is the r is equal to 4 sine 4 theta, the big question here is, how can we solve for the area enclosed by one petal of a polar curve? So, the first thing that we need to do here is to graph the equation, and we are already done with that. So we use the Desmos app to graph our equation, and plugging our equation, we come up with this graph. A flower. So in this equation, we have a total of 8 petals in this curve. So we only need to find one area of just one of them because they are all the same. And let's choose this one petal or one curve. And looking at this, how can we find the area of this shaded region? So this is the formula that we need to use. And the area is gonna be the definite integral from alpha to beta and 1/2 r squared d theta. So we already have a formula for r, and that is here in our equation, the r is equal to 4 sine 4 theta. Now, what is this alpha and beta? Let's look at our graph once again. As you can notice, the shaded region was bounded by the angle theta is equal to 0 degree and the angle theta is equal to 45 degree. This is our 45 degree, or simply pi over 4. So this angle is our alpha and this angle is our beta. And this is our r. So to prove that this is indeed, our beta and alpha is indeed bounded by the angle 45 degree or pi over 4 and the 0 degree, let's put it in the unit circle. So as you can see here, the beta angle is in the 45 degree and our alpha angle is in 0 degree. So therefore, the area will be the definite integral from 0 to pi over 4, 1/2 times r squared, or the 4 sine 4 theta squared d theta. So we have 4 squared is equal to 8 times 1/2, we will have 4, and we will put 4 in front. It will become 4 times the definite integral from 0 to pi over 4 sine squared 4 theta d theta. So to evaluate this definite integral, you first need to be familiar with the power reducing formula. For example, we have the sine squared theta is equal to 1/2 times 1 minus cos sine 2 theta. So if we have the sine squared 4 theta, what we will going to do here is we only need to double the angle, which is the 4, and the 4 will become 8, and the result will be sine squared 4 theta will be equal to 1/2 times 1 minus cosine 8 theta. So let's go ahead and replace the sine squared 4 theta into what we have here, which is the 1/2 times 1 minus cosine 8 theta. So our area now will become 4 times the definite integral from 0 to pi over 4 times 1/2 times 1 minus cosine 8 theta d theta. Now, we will multiply the 1/2 and the 4, which will be equal to 2. And our area now is, area is equal to 2 times the definite integral from 0 to pi over 4 times 1 minus cosine 8 theta d theta. Now, we are in the position to take the integral of this expression. So, what is the antiderivative of 1 or 1 d theta is simply 0. And the antiderivative of cosine is sine. And the antiderivative of cosine 8 theta is sine 8 theta over 8. So here is our equation. And we evaluate it to 0 to pi over 4. So now, let's replace pi over 4 into the theta, and it will become, the area is equal to 2 times pi over 4 minus sine 8 times pi over 4 over 8. And let's plug in 0 into our theta, and it will become 0 minus sine 8 times 0 over 8. It will be simply equal to 0. And 8 times pi over 4, it will become 2 pi. And sine of 2 pi is simply 0. So our area now will become 2 times pi over 4 minus 0. So it will simply become 2 over 4 pi or 1/2 pi. So this is our area for this one petal or one curve. Here it is. And that's it. So that's how we can solve for the area enclosed by one petal of the polar curve. And now let's proceed to the next presentation. Fighting!
So let's proceed with the definition of double integrals. So double integrals are a way to integrate over a two-dimensional area. In some cases, the integral of one variable function. So a double integral is defined as a limit of a Riemann sum. It is used to calculate the area of a region, the volume under the surface, and the average value of a function of two variables over a rectangular region. So So the double integral represents the integral of the function f of x and y over a given region R. Suppose that for a region R is defined by x, which includes a and b, and y, which includes c and d. We can define the double integral of the function f of x and y in the region R is given by the expression beside. Double integration of f of x and y dA. So the double integration, um, given the values of x and y, dx dy. So how to solve double integrals? So first, you're going to determine the limits of integration of the function in terms of two variables, normally x and y. Second, evaluate the inner integral by working on one variable while treating the other as constant. And then lastly, now you should work out the outer integral using the resulting expression. So let's proceed with the properties of double integrals. So there are four. The first one is the double integral of the absolute value of f of x and y plus and minus g of x and y dA is equal to the double integral of f x and y dA plus minus the double integral of g of x and y dA. The second one is the double integral of f of x and y dA is equal to k double integral of f of x and y dA, where k is constant. And the third one is when f of x and y is less than or equal to g of x and y within the region R, the inequality double integral of f of x and y dA is less than or equal to the double integral of g of x and y dA. And the last one, if f of x and y is greater than or equal to 0 within R, and the regions R and S are not overlapping each other, then we can write the double integral of f of x and y dA as shown below. So this is what you can see. So now let's proceed with the applications of double integrals. So first, we have the areas of bounded regions in the plane. So the area of a closed bounded plane region R is given by the formula area is equal to the double integral dx dy. So let R be a bounded region in the xy plane and f be a function continuous on R. If f is non-negative and integrable on R, then the volume of the solid region between the graph of f and R is given by volume equals double integral of f of x and y dx dy. Another important application of double integral is the calculation of surface area. Let S be the surface Z is equal to fx of x and y, where the points x, y come from the given region R in the xy plane. So this will be the formula for the calculation of the surface area. Now let's have the first and second moments and centers of mass. So mass and moments formulas for thin plates are covering regions in the xy plane. So we have the mass, as you can see the given formula, and then the density, first moments, center of mass, and also we have moments of inertia, second moments, about the x-axis, about the y-axis, and about the origin.
So today, I am tasked to show one problem that involves double integral. We have double integrals of f of x comma y dx dy, where r is the region of the integration in the xy plane. So double integrals give the volume under the surface given the function f of x comma y. So here we are now integrating over two variables, x and y. Each variable, we have an integration sign, as you can see here. And to indicate the variables involved, we have dx and dy. Dx is associated with the x integrand here, which runs from a to b, and dy is associated with the y integrand here, which runs from c to d. So let's try to find the volume under the function f of x comma y equals 1 plus 4xy, where x ranges from 0 to 1 and y ranges from 1 to 3, as you can see in the figure. The volume will be given by the double integral here. We will start with the innermost integral first and then doing outwards. So doing the dx integral inside first, we will treat y as a constant and then simply integrate the result with respect to y. So the integral of 1 plus 4xy with respect to x from 0 to 1. As you can see here, the antiderivative with respect to x is x plus 2x squared y, which we will evaluate from 0 to 1. Evaluate at x equals 1, we have 1 plus 2 times the quantity of 1 squared y minus the result when evaluated at x equals 0 is just 0. Therefore, the solution or the result is 1 plus 2y. So, after evaluating the first integral, we are left with the integral of 1 plus 2y with respect to y from 1 to 3. So the antiderivative with respect to y is y plus y squared, which we will evaluate also from 1 to 3. So evaluate at x equals 3, we have 3 plus 3 squared minus, evaluate at x equals 1, we have 1 plus 1 squared. So 3 plus 9 minus 1 plus 1, or 12 minus 2 is equal to 10. Therefore, the volume under the function f of x comma y equals 1 plus 4xy, where x ranges from 0 to 1 and y ranges from 1 to 3 is 10. That's all. Thank you.